So we'll start the session. Hello. So good evening, everyone. This is live discussion session for problem solving, number 7, and this is about the NPTEL course entitled Basic Thermodynamics, Classical and Statistical Approaches. And myself, Akash Gutal, I'm PhD student from Department of Chemistry, Indian Institute of Technology, Jodhpur. So in today's session, we will be discussing the problem uh, which are related to classes that you had done in last week. So first we will revise the things that we have completed in last week. So the classical part, classical thermodynamics is concluded, I think, from sixth up to the sixth week, and we have started the new statistical thermodynamics part from week 7 onwards. So this includes, so we'll start revising the things. So, so according to the second law of thermodynamics, we know the entropy of the universe is always increases, and we don't know the reason, the fundamental reason behind it. But by statistical formulation of the second law, of thermodynamics, we can give the answer to the question of why entropy increase is always favorable. So this answer to this question can be given by the statistical formulation of the second law. And so what statistical thermodynamics says to us is every system, if left to itself, will on the average change towards a condition of maximum probability. So this is the reason for the increase in the entropy. And from that, we defined what are the microstate, difference between the microstate and macrostate. And so in classical thermodynamics, we say whatever the variables related to the system are the macrostates, and whatever in statistical thermodynamics we will say it as the microstates. So everything is in statistical thermodynamics, it will related to the fundamental unit of whatever your states of the matter, which is atom within the atomic units, and that will give you the definition of different arrangement of atoms and molecules. So this is called microstates. The same in the statistical bulk matter, we use the same thing as macrostates. And in case when we are defining to the atomic level or the fundamental level of the your system, then how we describe the system is exact position and momentum, movements of atoms and molecules. But the same thing in case of classical or bulk matter case, we define it as in terms of number, pressure, temperature, or number, volume, temperature, etc. So in classic thermodynamics, we uh, study things in bulk, but in statistical thermodynamics, we will study to its fundamental unit, that is atoms and molecules. Let me add one slide. So then uh, after that we have seen what is sorry. So after that we have seen what is the one second. Let's just arrange the Boltzmann law for entropy. So entropy Boltzmann, what he said that what he discovered that the entropy is actually proportional to your number of microstates in the system. And from that, as the entropy, the number of microstate is actually very big number. You consider in your 1 mole of your substance, we will be having 10 raised to 23 number of atoms, entities, or molecules, or atoms, elements, whatever it may be. But this 10 raised to 23 number is actually is really large, and the microstates related to this 10 raised to 23 number is also large. And we know that entropy is an additive property when you uh, suppose the A having entropy SA and B system B having entropy SB, and we combine both system A and B, then your total entropy will be SA plus SB. Because it's additive nature, and S is actually directly proportional to natural log of uh, number of microstates. And after removing the proportionality sign, we know the constant that we get is the famous constant which Boltzmann have given is Boltzmann's constant into natural log of number of microstates. So this is nothing but the Boltzmann's equation, Boltzmann's entropy equation. So it's one of the famous equation. All the statistical mechanics and statistical thermodynamics that we see is actually the basic fundamental equation is the same that we that's the Boltzmann entropy equation. It is having the same significance that uh, we know that the relation between energy and the mass. That's the Einstein's equation of relativity in the relativity. But the same kind of significance in statistical thermodynamics can be given to this equation. So that kind of important equation it is. So next part we had seen is that the probability. Then we discussed about the probabilities. So in case of probability, suppose event A and B, see, if A and B, we need to calculate probability of event A and B, then the probability equation will be, let's say x and y. It's better to calculate x, y. Then probability of event x and y will be probability of x probability into probability of y. And if it is x or y, then probability of event x or y is probability of x plus probability of y. Right? And at the end, we will be having equation of permutation and combination. So equation for permutation is n r equal to n factorial divided by n minus r factorial. And similarly for combination is n factorial divided by n minus r factorial. So n2 r factorial. So these things we have covered, and let me add one new slide. So next thing we have seen that the microstate, concept of microstate. And we have defined the most probable state is that for which the entropy is maximum. So S is maximum in the sense W is max. The number of microstates are max. So, so, so the condition of the system where the total number of microstates having its maximum value is the stable or most probable state of that system. So system always want to maximize its number of microstates. So, and that is related to your spontaneity. In spontaneity also you will see this free expansion of gas. If you consider, the gas will expand and its volume will increase. This happens spontaneously, and increase in volume actually gives you more entropy once the volume is increasing, which means the number of microstates are also increasing. So that's why any process which is a spontaneous is actually having this hidden thing that its number of microstates are always goes to its maximum value. Right? So these are things that we have covered last week, and let's solve some problems related to this probability section. So the question number one is, if a dice is rolled four times, what is the probability that six comes up at least once? So if you can solve this problem, you just start solving this problem on your own. I will give some time. If you can solve, able to solve, you just tell the answer, or you can put the answer in the comment section, comment box. So we are going a little slow because this is probability section. Uh, the problems really need to we need to understand it first and then need to solve. So if you try by yourself, you can try. I'll give some time. So this is the question related about dice, and the dice is rolled for four times. And what is the probability that six comes up at least once? So remember, this question is about uh, and or probabilities for the events. So I will start solving. So we have dice which is rolled for four times, right? And we want to know the probability that the 625 point divided by 12. Oh, no. Do it again. You are close to the answer. It's not the answer. So that six comes up at least once. So suppose it can come at in the beginning of the first time, and all other three will be left with different numbers. So how many combinations that this thing can lead to? So let's say for 6 appearing for only once is can be it can happen. This is second, third, and fourth time. And and this circle means all other values can appear there. Except 6. Okay. All other 5 values can appear there. And similarly, for 6 appearing for twice, we'll be having 6, 6, and similarly 6, 0, 6, 6, and only 0, 6, 6. Fine. And if 6 appearing for 6 times, 3 times, then we can say 6, 6, 6. Similarly, 6, 6, 0, 6, 6, 6, 6, and 0, 6, 6, 6. 3 times it can appear, and at the end it can appear for all the 4 times. 4 times it can appear only for once. So only we need to consider in the first case, as we can see 5, 5, 5, uh, 5 different numbers can appear at the second, third, and fourth place. So the total number of their combination will be 5 into 5 into 5, which is nothing but 120. In the same case for all these 4, fine, will be 125, 125 in all the 4 cases. And in second case, this will be the third and fourth place can be taken for by five different uh, numbers. So it will be 5 into 5, which is 25 combination. So it's nothing but for rest of all 2 to 6 appearing for twice, we having 25, 25 number of combinations. In case of in third case, where 6 appearing for thrice, we'll be having only 5, 5, 5, 5, 5 number of time it can appear, and at the end only 1, 6, 6, 6 can appear. All 4 times 6 happening is only it can happen only for once. And so if we add everything, we have 125 into 4 plus 25 into 1, 2, 3, 4, 5, 6. 2, 6 plus 5 into 4 plus 1. That will gives you 500 plus 150 plus 20 plus 1. That will be 671. And the probability of appearing of each number is 1 by 6. And we know this is and probability scheme. And means 1 by 6 cross 1 by 6 cross 1 by 6 for 1 by 6, which is nothing but 1 by 1296. And we know what is So from 12 9, so the probability should be 671 divided by 1296. So there are 1296 number of combinations, from which 671 that we have calculated will be probability of 6 comes at least once. So the probability will be 671 divided by 1296, the total number of combinations. So answer must be 1. So the next, we move towards the next question. So two cards are drawn from a deck of 52 cards without replacement. So it is without replacement. What is the probability that both are hearts? So take 2, 3, 4 minutes to calculate this and tell me the answer if you get it. So this question is also related to and events and A and B events. So probability should be multiplied. So we are having two cards. We are drawing from 52 cards without replacement. Okay. So so we know that we are having total 4 different types, which gives you for each for hertz will be having total 13 cards. Sorry. Huh. Hertz will be having 13 cards. Fine. So your probability of drawing first card. will be, and that card being a hard is 13 by 52, because total 13 number of hearts are there in one set. And when you're drawing at the second time, because you have drawn the first card in the first place, you will be having only 51 card left in your set. And from that, we are drawing one uh, card. And also, uh, the first card, if it is hearts, then it should, the remaining hearts card will be 12. Fine. Then the probability of getting hearts is 12 by 50, 51. Fine. For second card is being heard. So this is depend upon the first event. First event, if it is hearts, then that card will not be replaced. And for the second time, when you are drawing the card, then you must be having one less heart card, and also the total number of set one less card. And this event is, as it is an AND event, so the probability will be into 12 by 51. The two events, probabilities of two events will be multiplied. So what we are getting is 4, 4 to the 12, 3 by 51. So probability of that the both cards are hearts is 3 by 51. So your option is, I think, option number 3. Fine. So the next question. Next step. So there are 7 distinguishable particles and 5 distinguishable boxes. What is the total number of microstates? So try to solve it. Take your take your own time, 3-4 minutes. So, so this box and particle problem, we have formula for number of microstates. For n number of boxes, and if we want to distribute with 7 eh, r number of particles, so that formula is just n raised to r. If you do 5 raised to 7, so that if you do comes out to be uh, so this comes out to be 78 125, and so answer must be 78 125. So the next question is, suppose two cards are drawn from a deck of 52 with replacement. So remember, it is with replacement. What is the probability that all have the same values? Now it is not asking about the hearts or diamonds, but it is about the same values. So what is the probability that all have the same values? So remember, these two cards are drawn with with replacement. Right? So two cards are drawn from a deck of 52 with replacement. What is the probability that all have the same all have the same values? So we know that in each set that with 52 set, we have nearly four cards which are having same value. So your probability of the first draw uh, is the number can appear, that is 4 by 52. Probability is 4 by 52 is nothing but 1 by 13. And the second times when you are drawing the card, because we are replacing the same card, then it should be 1 point. The probability should be the same, which is nothing but 1 by 13. So the total probability must be 1 by 13 cross 1 by 13, as it is AND event. Answer should come 1 by, I think there is no option. 1 by 13 divided by 13, 0.59. Okay. It's appearing as 0.59. 2 by 13. Uh, 0.0059. Something is, I need to check the options again. Options is not matching. So we'll move towards the next question. So the question number 7 is, an instructor gives her class a set of 10 problems with the information that the final exam will consist of a random selection of 5 of them. If a student has figured out how to solve 7 of the problems, what is the probability that he or she will answer correctly all the 5 problems? This last problem I will check and let you know. The answer is not matching. So solve this new problem. So here the instructor gives her class a set of 10 problems. Uh, and he wants to select it randomly 5 problems of them to evaluation. And if a student has uh, figured out how to solve these 7 problems, so we need to calculate the probability that he or she will answer correctly all the 5 problems. So here we need to use the combination method. So I'm giving you hint. You need to use combination. Try to solve. So an instructor gives her class a set of 10 problems with the information that the final exam will consist of a random selection of 5 of them. So if student has figured out how to solve 7 of the problems, then what is the probability that he or she will answer correctly all 5 problems? So this question can be answered. So there are 3 aspects for this question. Let's solve it stepwise. The first will be, so find the total number of total number to select 5 problems. So find the total number of select 5 problems, which is nothing but we need from 10 problems, we need to randomly select 5 problems. So that will be 10C 5. That is NCR, that is combination of 5 will be 10C 5. So that will give you 10 factorial divided by 10 minus 5 factorial into 5 factorial, which is nothing but um, 10 cross 9 cross 8 cross 7 cross 5 factorial, 7 cross 6 cross 5 factorial divided by 5 factorial into 5 factorial, which is nothing but 10 cross 9 cross 8 cross 7 cross 6 divided by 5 cross 4 cross 3 cross 2 and 1. 5 sa 3 sa 4 sa 2 sa 4 20 12 into 21, which is 252. Okay. So the total number of selecting the 5 question from the randomly from the 10 question is the 252. Okay. These are total number of ways. Fine. Let me add one new slide. And the second part we need to calculate is, sorry, second part we need to calculate is finding out correct correct answers, correctly answered all 5 problems. So whatever the student have figured out from 7 problems, well, so taking out 5 problems which are uh, correctly answered. So that will be 7C5, 7 factorial divided by 7 minus 5 factorial into 5 factorial. That comes out to 765 into cross 3. Okay, we have 5 here. So 5 factorial will be here. 7 minus 5 is 2 factorial into 5 factorial, which is nothing but 21 ways. Okay. And at the end, what we can do? Third is calculate the probability. So that probability will be finding out correctly answered all 5 problems, which is nothing but 21. Because student has solved 7 problems. He figured out 7 problems, he solved, and choosing 5 problems from that 7 problem. How many combinations can happen? So these are 21 combinations. And whatever the combinations for from getting 5 problems from the given 10 problems is the 252. So the probability will be 21 divided by 252, which actually if you calculate it by calculator, it comes up to be 21 divided by 252. So it's 0.0833. 0.0833. The answer option is option number 4. Fine. So the next question is, there are n socks, 3 of which are red, in a drawer. What is the value of n if when 2 of the socks are chosen randomly? Probability that they both red is 1/2. So take your own time to solve the problem. So there are n socks, 3 of which are red. So when we two of them are chosen randomly from the n socks, and the probability that these two will having color red is half. So we need to calculate uh, reversely what is the number of n. Take your own time. So I will take 3-4 minutes to calculate. Let me check recording. Yeah, so fine. So there are n socks, three of which are red in a drawer. So there is a drawer. So there are n number of socks, and from them three are red. Fine. So what is the value of n when the two of the socks are chosen randomly? If n socks are there, we need to choose two. So we need to take out the combinations of two. So how many combination from the n socks we can get two different socks is nothing but combination of NC2. Right? So this is the total number of possible outcomes. Outcomes in the sense, so this number of NC2, number of uh, different types of uh, outcomes we can get when we draw two socks from randomly from the draw. And this will be, and from the three which are already having red, what is the number of uh, possibilities that we can draw two from them, from these three red sources? Nothing but the 3C2, which is 3 factorial divided by 3 minus 2 factorial into 2 factorial. It's nothing but 3 cross 2 cross uh, now 1 second. It's just, so we need to calculate which is what three of which are red in the dot. And okay, then this red is 1 by 2. Fine. Uh, yeah, yes, I was right. So 3C2, we need to, yeah, 3 factorial divided by 3 minus 2 factorial into 2 factorial, which is nothing but 3 cross 2 cross 1 divided by 1 factorial cross 2 cross 1. So that will be is nothing but 3. So we need to calculate the probability. So sorry, we have the probability, which is nothing but total number of ways we can take two red socks from three red socks divided by total number of ways we can take two socks from 10, sorry, n number of socks. This is given as 1 by 2 in our information in the question. Let me add one new slide. So this is given is 1 by 2. It's 1 by 2. And we have NC2. We have NC2 is equal to n factorial divided by n minus 2 factorial into 2 factorial. So which is nothing but if we write it 3 divided by n factorial divided by n minus 2 factorial into 2 factorial. If 2 goes up, then it will form 1 half 6 divided by n factorial divided by n minus 2 factorial, which is nothing but, and if you do n into n minus 1, we can write it like this, which will be taken, will cut out, and we will having 1 half 6 divided by n into n minus 1, which gives you n into n minus 1 is equal to 12. And if you even you directly you can tell this n is equal to 4, because 4 across 3 is 12, right? 4 into 4 minus 1 is 12. Hence, your n is 4. The number of socks are 4. And your answer must be option number A. So the next ninth question is the entropy of particle in bag A is 2.6 kb, and that of bag B is 8.3 kb. If the particles can now move between bag A and B freely, then the new entropy is. So this is simple question. You just take 2 minutes, 2 3 minutes. It's fine. So in this question, the entropy of particles A and B are given. The given things we will see. The entropy of A is 2.6 kb. Entropy of B is 8.3 kb. And as we know, the Boltzmann entropy equation, S is equal to kb ln W. So what we are having, this 8 point coefficients are nothing but logarithm of microstates. And we know entropy is additive. If suppose we mix these two systems, bag A and bag B, freely, uh, so the particles can now move between a bag A and bag B freely. Hence, our total entropy should be SA plus SB, and that turns out to be 2.6 kb plus 8.3 kb, which is 10.9 kb. Answer is answer number B. So the next question. So there are two distinguishable levels and six distinguishable particles. What is the number of microstate in the most probable distribution? Please try to solve it. So we have here two distinguishable particles. Sorry, six distinguishable particles and two distinguishable levels. So we have two level system and we have six particles. One, let me wait. Symbol 1, 2, 3, 4, 6. Right? And we need to distribute in these two levels. So how we can distribute? So let's say we have distributed 6, 0, okay, 5, 1, 4, 2, 3, 3, 2, 4, 3, 1, 5, 0, 6. Right? That will be the probable distribution. And we need to find out what is the most probable distribution. So the most probable distribution will be having most this W value, which is nothing but n factorial divided by n1 and 2 factorial and 3 factorial dot. Number of levels depend upon number of levels. So n factorial here is nothing but the total number of particles divided by n1, n2, n3 are the numbers of particles in respective levels. So we will calculate for every level. You calculate for it at every level is n factorial is 6 factorial divided by 6 factorial. That will be 1 for so is for 0 6 0 1 W0 W15 will be 6 factorial divided by 1 factorial into 5 factorial, which is nothing but 6 W24 6 factorial divided by 2 factorial into 4 factorial, which is nothing but 6 cross 5 divided by 2 cross 1, which is 3, 15. Then we have W of W of 3, 3, but nothing but 6 factorial by 3 factorial into 3 factorial, which is nothing but 6 cross 5 cross 4 divided by 3 cross 2, which is nothing but 2 and 2, 20. Similarly, if we go W4 2 will be the same as that of 15, same as that of W24. W51 will be same as that of 6, which is nothing but W15. And this will be the same as that, and W60 is also same as that of W06 is equal to 1. So we will be having maximum W value is for 3 combination, which is microstates, number of microstates are 20. So answer must be option number 4, which is nothing but the 20.